Hey there, everybody. Welcome back. We're almost done. Today's polar coordinates. Who here did not take Math 54? It's called Pre-Calc B now. It used to be trigonometry. Did anyone not take it here? Okay. I know you didn't. You weren't here. Have you worked with polar? Those of you that haven't, have you worked with polar coordinates before? What they are is instead of using X, Y, we go to R theta. You know, okay, so I'll go through the full spiel. Was curious who had not seen it. Because some students get here and get directly into calculus and didn't have trigonometry at high school. And this is like one of the last topics taught at trigonometry. In fact, I taught this lecture this morning in trigonometry. It's fucking bizarre. Like, I'm like, oh my God, this is the same shit.
Were you going to include probably the last one?
I actually uploaded it.
Oh, perfect.
Yeah. And if we have time at the end, we'll go over it at the end. All right, so going through this, let's start with A. How do I do A here? This is working polar coordinates, practicing with sine and cosine seems like a good warm-up idea. How do I find arc length? In parametric form. Okay. So we'll take the derivative of x with respect to t, and I get cosine t minus sine t. And dy dt is cosine t plus sine t. Now what? It's from 0 to pi, and what am I doing with this? Just you can do the general form right here. Yeah. What are you memorizing already? Good. Excellent. I'm thinking going to SI sessions is working out good for you. So since we're going to have to square them and add them up, let's do that shit before we throw it under the integral where it's just having to rewrite all the integral shit. So what happens if I square this bad boy? I get cosine squared t minus 2 sine t cosine t plus sine squared t. That's dx dt squared. And dy dt squared, we're going to get cosine squared t plus 2 sine t cosine t plus sine squared t. Right? I jumped through it a little quick, but when you square them, don't forget you don't just square each thing individually. You got to find there's a FOIL thing going on. So if I add these together, well, before I add these together, dx dt squared kind of simplifies a little bit, doesn't it? What does that equal? What simplifies as part of it? Wait, what? This part does simplify. It turns into negative 2 sine, nope, negative sine 2 theta.
Oh.
But what about cosine squared and sine squared? Oh, y'all don't remember. 1. C squared plus S squared is 1. So those turn into a 1. Sine of 2 theta is 2 sine theta cosine theta. So that's not going to really help us because if you notice, dy dt is going to have the exact opposite thing. We're going to have sine of 2 theta, the positive version, plus 1. So when we add these together from 0 to pi, let me put t back in. I said theta. Dt. Those just cancel out, don't they? And I get 0 to pi of the square root of 2. So if I integrate this, I got 2t root 2 from pi to 0, and we get pi root 2 as our answer. All right, what about B? So x equals cosine t. So dx dt is negative sine t. Y was 1 plus sine t. So dy dt is cosine t, which means dy dx is cosine over sine, which is just negative cotangent. That looks weird, cotangent t, having 2 t's in a row. It's tripping me out. Everyone okay with that? This was from the last lecture. Remember, dy dx is dy dt over dx dt. And then the second derivative was ddt of the first derivative over dx dt, which was negative sine t. What's the derivative of cotangent? Sounds about right. Cosecant squared. Shit. Is cotangent you have negative cosecant squared? I don't remember. I'm brain farting here. Someone help me. It has the negative part of it. All right, we'll make it positive then. That's how often you work with the derivative of cotangent. So what is this? It's just negative cosecant cube t. And we want to find the tangent line at t equals 5 pi over 6. Well, we can plug 5 pi over 6 into dy dx. M equals negative cotangent of 5 pi over 6. That is 150 degrees, reference angle of 30. I think this is easier to see as negative cosine over sine, because I don't remember these very well. This is negative It's already negative. The negative is going to cancel out √3/2. And that one is 1/2. So m is just √3. You get that? And what is x and y at that value? X equals cosine of 5π/6 is negative √3/2. Y is 1 plus sine t, sine of 5π/6. It's just 3/2. So I get y minus 3/2 equals the square root of 3 times x plus the square root of 3/2. And now we have our line. That was part B. I didn't actually write. All right, that kind of like reinforced some of the stuff we did in the last section. Why am I doing that? Well, we're going to do this again on Monday, but we're going to do it in polar coordinates on Monday. And that's why we're covering polar coordinates today. This is mostly a recap, unless you've never seen it. And if you haven't seen it, it'll be new. Did anyone need that up longer? Okay. So polar coordinates. It's desirable to be able to work in polar coordinates sometimes. I don't think I spelled that right. That looks better. To work in polar coordinates, both for integrating weird regions and graphing some complicated shit. Polar coordinates are of the form r theta, which is the angle. And we're going to be able to switch back and forth from that to our rectangular coordinate system, xy. Polar coordinates are great for circular shit. When we hit 3 dimensions, now we're looking at cylinders like cans, tubes, pipes, lots of stuff comes in cylindrical shape. And we will upgrade this to 3 dimensions in Calc 3. So how do we do it? It's based on the circle of radius r has the equation x squared plus y squared equals r squared. And we can find theta by doing tangent theta equals y over x. if you ever don't remember it, hopefully you remember the Pythagorean formula. And you can just draw a picture of a circle, a radius r. This distance here is x, this distance here is y, and the angle is theta, and you can pull what you need directly from the picture of the circle. You will also see that we get x equals r cosine theta, and y equals r sine theta. These tend to be used to switch to polar. Now, switch from polar. More often. And this is used to switch to polar. So let's just do some quick examples of converting to rectangular coordinates or polar coordinates. For those of you that didn't take trig here, this is useful. Let's switch -2, 2√3 to polar. Well, if I want to switch to polar, actually, I guess this description isn't helpful. Because getting r is much easier if we just use x squared plus y squared. R squared is going to equal x squared plus y squared. So r squared is -2 squared plus 2√3 squared. This is 4 plus 12. So r squared equals 16. When you're working in polar, -r is fine. So this is going to give us r equals plus or minus 4. And we're going to keep both of them. And I'll show you why in a second when we graph them. And if I want theta, we're going to do tangent theta equals y over x, 2√3 over -2 over x. So tangent theta is -√3. Where does tangent theta equal -√3? What? It's got a reference angle pi over 3, yeah. But it's negative, so it's got to be in quadrant 2 and quadrant 3. That's pi over 3, that's pi over 3. So the theta is going to be 2 pi over 3 and what, 5 pi over 3? And since we start with tangent theta, both of them are valid here. But which one are we actually at? X equals -2 and 2√3 is in quadrant 2. So to write this in polar, I can either do theta is 2 pi over 3 and r is +4. Or I can rotate all the way around to 5 pi over 3. And this is where the negative r comes in. 5 pi over 3 is in that direction. Negative r means we're going the opposite direction, that distance. So we would, if we want to end up over here, but we're doing that, we got to have a negative radius. This is where the -4 comes in. Those are the two ways to write that coordinate there. So -2, 2√3. Switch to 4, 2 pi over, oops. Or, make sure I'm on the screen, 2 pi over 3. Or -4, 5 pi over 3. But working in cylindrical, or not cylindrical, polar, if I go a full 2 pi around again in radians, I'm back at the same point. So actually, this is any multiple 2 pi over 3 plus 2 pi k. Or -4, 5 pi over 3 plus 2 pi k. So to summarize graphing in polar, to graph in polar, rotate theta counterclockwise from the positive x-axis. This is called the polar axis, or pole. And then B, go r units in that direction. Where -r, where r is less than 0, means go in the opposite direction. And I'll show you how to graph using the one we just had. Put it back down where we can see it. So the XY graph has a bunch of rectangles on it. The polar graph has a bunch of circles on it, centered at the origin, equally spaced. If you're sketching this by hand, I'd start with the inner circle. It's a little bit easier to try to keep your line going around it equally distant from it if you have the inner one, and the inner one's a little bit easier to draw as a circle rather than starting with a big S circle. And then I'm going to put in 30-degree marks. It oftentimes looks like this spider web. Actually, I should where those were already. We already know where that results in. Let me give you some different points for these. Let's do point P, I don't know, at 245. See, let's make sure I got each set up. Let's do Q is at 3 negative 30 degrees. R is -1. Let's say 5 pi over 4. And we'll do S is at -3 negative pi over 3. So for 45 degrees, we rotate 45 degrees, which is about halfway between the 30 and 60 mark. And we go out 2 rings and put a point. That would be point P. For Q, I'm going to rotate -30 degrees, which is along this axis. And we're going to go from the center, we're going to go out 3 steps. And that'll be our Q. Everyone with me so far? 5 pi over 4 is in quadrant 3, this direction. And if I go -1, I'm actually going to go this direction, this way. So R is going to end up right next to P. So we're going along the -5 pi over 4 line, and we're going to go -1 in that direction. And negative pi over 3 is the equivalent of negative 60 degrees. That's this line. And we want to go negative 3, so we're going to go the opposite direction. 1, 2, 3, that would put S right there. Switching from polar to rectangular is a lot easier really than going the other direction. If I wanted to write S in rectangular, well, for S, my R is negative 3, my theta is negative pi over 3. And recall x equals r cosine theta, y equals r sine theta. So I have x equals negative 3 cosine of negative pi over 3. And y equals negative 3 sine of negative pi over 3. That is 1/2. So we get negative 3/2 for x. Negative sine of 60 or sine of 60 degrees, negative 60 is negative root 3 over 2. So this is positive 3 root 3 over 2. And I get the coordinate negative 3/2 3 root 3 over 2. Which does line up with the quadrant that we have. All right, so that's the idea of how polar coordinates and polar graphing work. Let's take a look at equations. Any questions so far? All right, so like examples where polar going to polar for graphing is good and bad. If we had the equation of the ellipse x squared over 4 plus y squared equals 1. This goes out a unit 2 in each direction here, a unit 1 in each direction here. Wrapping this in rectangular is super fucking easy. If we switch to polar though, I'm gonna clear fractions here by multiplying by 4. And I'll get x squared plus 4y squared equals 4. And we'll substitute in what we have for x, r cosine theta squared plus 4 times r sine theta squared for y equals 4. And generally we write, like normally we do like for lines, we do y equals mx plus b. We make y a function of x. We tend to do the same thing for r as a function of y. or not y, theta. So we isolate r. So if I distribute that square, I've got r squared cosine squared theta plus 4r squared sine squared theta equals 4. And we can factor out the r squared. Yep, I'll just stay right where I'm at. We'll divide by that multiplier, the cosine squared. And finally, we'll take the square root. And I realize the top cleans up a little bit, but top is going to be 2. The bottom doesn't clean up. To graph in this form, what you kind of have to do is go make it like an XY table would make a theta R table. So like theta equals 0 degrees or radians. I think it's easier to think in degrees for this. R is going to be a clusterfuck, right? Well, the bottom is just 1. Actually, this ends up being just 2. And we know that going 0 degrees gets us to the 0.2, a radius of 2. But if I wanted to go like 45 degrees, R equals 2 over cosine 45 squared plus 4 times sine of 45 squared. And it starts getting messy. This is messy. I'm going to say stop. Stop. Messy. Not really useful. So you should really only try graphing in polar when it's going to help. In some things it's going to help because you'll have no idea how to graph the other thing. As we'll see with plenty of the things we're going to have today. For example, square root of x squared plus y squared equals tangent inverse of y over x. I think we can all agree, Buck, making an XY table for this. I'd have to isolate one of the letters to make this useful. This is fuck. Hell no. Like, nope, not doing it. A big fat hell no. But if I switch to polar, this is R equals theta. And now for doing this, we don't actually want to use degrees because radians are an actual number, whereas degrees have a symbol on them. So if I made a table here of theta and R, 0 is 0, pi over 4 is pi over 4, pi over 2 is pi over 2. I think we can see where this is going. what you get, I'll try to put the circles in light. Oh, it doesn't show it very well, green. God, those are some shitty circles. Pi over 4 is what, like 3 point, it's about 0.8. This is about like 1.6. I'm doing some serious rounding here. But like, we're not getting precise, we're just trying to figure out where the shit goes. So going 0 degrees and outer radius R gets me the origin. But if I go pi over 4 and out 0.8 degrees, I'm right here. That's along the pi over 4 line. Pi over 2, I go out 1.6 is up here. Pi would get me to pi, which is 3.14. Let's say 3.1. 1, 2, 3, a little bit out here. Three pi over 2. It's kind of like adding these two together, about 4.7. So 1, 2, 3, 4, like down here. And 2 pi would put me at 2 pi right there. And it keeps going. It's a spiral that's getting bigger as you go out. But this looks too clean in a spiral. It's like lopsided looking when you actually plot it. I want to say this is called the spiral of Archimedes, I think. Or it's related to the spiral of Archimedes. I have that in my head. I don't know. I think it might be negative theta for R. I don't know. We could plug in negative angles, right? And it's going to make it rotate the other way. If I did negative theta, or theta is less than 0, I start going the opposite direction. Like theta is negative pi over 4. I get negative pi over 4. So I'm going along this axis, but going that way. What it does is it spirals out and does some shit like this. I think it hits there, the cross here, keeps going like that. And you get this weird like shit going on, depending on how you do theta, how far you go out, negative and positive. Kind of crazy looking. This was much simpler to graph than trying to figure out an XY table for this, right? Y equals √3 over 3x is a line, right? We can do that. Where when I go out X equals 1, I'm going up √3/3. What is this in the other form now? R sine theta equals √3/3 R cosine theta. And although we know can equal 0 here, clearly it does. I'm going to ignore that fact and still I can divide by R. Just to show that it's not really necessary in what we're getting here. If I divide both sides by cosine, I get tangent theta is √3/3. Which now in hindsight, I see I could have just done y/x equals √3/3 and made the substitution that way. Because that's tangent theta. But what does that make theta here? Pi/6. The equation of line, that line is pi/6. Theta equals pi/6. No. Yes, of course. In general, lines are not worth switching. Don't switch lines. Lines are fucking confusing and polar. For example, a vertical line I write it down here. What is it? Well, I know I'm going like a vertical line is x equals a. Going down a. And x equals r cosine theta. So r cosine theta equals a. And this is just a clusterfuck. Not helpful. If I had the horizontal line like y equals b, r sine theta. So r equals b over sine theta. The big reason I'm pointing these out to you is like, if you see these in polar form, like a over cosine theta or b over sine theta, switch to rectangular to graph if you want to keep your sanity. These two aren't a whole lot cleaner. Switching to polar here isn't really a lot cleaner. Other than I can do like 30 degrees, I can estimate that a hell of a lot better than I can estimate √3/3 and like figuring out how far over and up I gotta go. What about something where we're in the form of R equals? Like, what about R equals 2? I don't have any information about theta, so go ahead, Michael. It's just a circle. It can be any theta. R equals 2 there, it's 2 here, it's 2 there. So R equals 2 is just a circle, which we would see if we squared this, R squared equals 4. And R squared was X squared plus Y squared. So we can see that. Let's take a 10-minute break and then we'll start doing the shitty ones. There's a bunch of names for them. I'll show you. All right, so we've got a bunch of fun shapes that we're going to look at. I'm going to show you the screen. I'll show you what I fucking Googled. Because like writing all these down is a waste of your time. They're not worth memorizing. It's important to know that there are differences. So let me switch this over and change the video here. I looked up crazy polar graph shapes. That's literally what I looked up. Crazy polar graph shapes. Mathematics LibreText popped up a good one. There's even more going on there. This talks about doing some stuff, how it, Kepler's laws of planetary motion, they follow ellipses. So it uses some of this shit. But the graphs that I want to show you, if you can scroll down to the very bottom here. Almost there. So we're going to graph some of these. Circles don't have to be centered at the origin. And what you're going to do is make an R theta table, plug in values of theta, find out what R is, basically for all of these. I wanted to point out that like the lemicon category is kind of like, it's called a lemicon. It's got this weird like fucking, I don't know what the character's called. It looks like a little hook under the sea. I think it's French. But all of these fall under the same form of a constant plus or minus another constant times cosine theta or sine theta. But sometimes they're going left, sometimes they're going right. Sometimes they make this heart shape, which is called why it's called a cardioid, like cardiac is heart. But sometimes a lemicon ends up with a loop inside, and it can even end up with a dimple. And I'll scroll up to show you that. The lemniscate looks like the infinity symbol. And both, like having cosine 2 theta and sine 2 theta is where it stems from. A is just some constant in the front. Obviously, having a perfect square makes this easier to graph, but you could have 3 cosine 2 theta and just have to have like a square root of 3 in there. The roses fall into these similar patterns. They're both here cosine n theta. If n is odd, it makes a rose with n number of petals. If n is even, it makes a rose of 2n number of petals. That's only helpful to remember like what it's going to look like. You really shouldn't rely on that kind of thing for plotting this. You should just make a table. We saw Archimedes' spiral earlier. We did this ourselves. Oh, I guess he had theta was greater than or equal to 0. We plotted it going the other way too. I thought it looked better going the other way. I like having both of them. In the lemicon category, we can also have, notice how we can have the infinity signs at angles, like the sines give us diagonals and cosines give us up and down, left to right. You're not going to remember this shit. It's just too much shit to remember, and you use it so rarely. Like I was struggling to come up for examples for this, like where you use this. There's not really even a lot in Calc 3 for the names of these things. The tools that we're doing, we're going to use a lot. Having a plugin, which is doing these things, is basically doing a parametric equation where our parameter is not t for time, but it's the angle theta. So this is another form of parametric equations. And so practicing this shit is good. Here's where we have a constant plus a constant times sine. And it looks like the heart, but the heart doesn't touch zero like it did in the other ones. It's got a dimple. It doesn't come all the way down. So you don't automatically just assume that if it's got like a plus b sine theta or a plus b cosine theta, that it's going to hit the origin. You're really just better off plotting shit. Okay. There's also other fun ones like the asteroid, spelled no shit. Like the planetary thing, the things that hurtle through the sky has TER right here, not TR. It's called asteroid because it's astro is star. It's star shaped. It comes from that fucked up equation right there. X to the 2/3 plus y to the 2/3 equals a to the 2/3. When you throw it into polar, I mean, they've got it as t here, but this is really polar when you got. It makes it's easy to see. It's much easier to plot the shape. It makes a star. All right, so back to the drawing board. Some things to keep in mind. Do not rely on this because if you misremember it, it fucks you. And sometimes in like some areas in Calc 3, it might screw you up on the R. For things that are graphs that are symmetrical about the x-axis, well, that are symmetrical. I'm going to say A about the x-axis. If I plug in negative theta, I get the same equation as with theta. In that category, like the lemniscate, which is a weird word, like R equals 2 cosine 2 theta falls in this category. Cosine is an even function, so if you stick in a negative, it's the same value as the positive. So 2 cosine negative 2 theta is still just the same value as that. And that's where we get the symmetry over the x-axis. Nice little reflection across x. If you did it, you could plot just part of it and reflect across x. The book is going to recommend doing that. I'm going to recommend you don't. It's a bad habit to get into. You can't rely on it. But it will help you, if you remember it, recognize this outcome should be supposedly symmetrical about it. When we go to Calc 3, it's going to work fine in this. In Calc 2, it's going to work fine. 2 dimensions, it's going to work fine all the time. Working in 3 dimensions is kind of. If we want symmetry about the y-axis, replacing theta with pi minus theta doesn't change the equation. you can see R equals 2 cosine 2 theta falls in this category. 2 cosine 2 theta. I'm going to write this, I'm going to treat that as theta plus theta on the inside for a second. So 2 cosine theta plus theta, doing a little trig, I get 2 cosine theta cosine theta minus sine theta sine theta. It's that kind of idea. We're going to do something like that. If I plug in pi minus theta, though, this is 2 cosine 2 pi minus 2 theta. So I'm going to follow the same pattern. Like if this is A and this is B, the plus is going to turn into a minus here. If I do this, I've got 2 cosine, the first one twice, plus cosine of the second one twice. This is a little weird because it's going to take a little work. Cosine of 2 pi is what? 1. This is 1 plus cosine squared 2 theta. Did I fuck something up here? I feel like I did. 2 pi minus 2 theta. Yeah, I did. I totally fucked this up. This is negative 2 theta here, and this is 2 pi here. Sorry, I fucked that up. It's cosine A, cosine B. And I really fucked it up. The second half is sine. R equals 2 cosine A, which is 2 pi, cosine B, which is 2 theta, plus sine of 2 pi, sine of 2 theta. I really showed my skill with that fucking equation. I went too fast is what it was. I know these equations. Just went too fast. And as Michael just got done saying, cosine 2 pi is 1. What is sine of 2 pi? So this just simplifies right back down to 2 cosine 2 theta. So that's where the symmetry is coming in. There is ones for symmetry about the origin, but that is just confusing as fuck for most people. It's not worth pointing out. You guys ready for some examples? Don't really rely on this symmetry, but it is helpful as for like recognizing if you took if you really want to take the time, you plug in pi minus theta and see if you get the same thing. Let's be honest, how often do you, this is a lot more work. Symmetry about the x-axis you can generally spot fairly quickly. This one takes work to fucking identify, as you can see here. So like, what if we had something like r equals 4 sine theta? Let's see, make a theta and an r. It might even be more helpful to do a sine theta column first, and then a 4 sine theta column for r. I recommend doing radians because that's what we're doing. R is going to be well, I guess not. For quadrant 1, I'll just bust through some of these in quadrant 1. 45, 60, 90. Maybe we'll look at 135 and 180. We'll see if we need more. So both sine of 0 and sine of 180 are 0. Sine of 30 degrees is 1/2. 45 is root 2 over 2. 60 is root 3 over 2. 90 is 1. 135 is the same as 45. We got root 2 over 2. So if I multiply these by 4, I get 0, 2, 2 root 2, 2 root 3, 4, 2 root 2, and 0. I don't know what the hell 2 root 2 is, or 2 root 3. About 2.8-ish and 3.4, I think. 2 root 2, 2.8-ish. And 2 root 3. I guess it rounds, it's closer to 3.5, not 3.4. So it looks like if I'm doing this, I need to go out, I need to have 4 rings because my radius goes up to 4 here. Do the green line is my 30-degree marks. I'll just do this, make the cross tag like that for the 45-degree marks. And we start putting in some points. I got 0, 0. When I go 30 degrees, I'm going out to 2. That's not 2, that's 2. 45 is about 2.8. 60 is about 3.5. And 90 degrees is 4. So it looks like it's going like this, and make a nice little curve. If I do 135, I'm going out approximately 2.8. Looks like it's symmetrical with the other side. So I can probably copy some of the symmetry from the other side here. And 180 is 0 again. It's a fucking circle. Does going further help? Let's check. If I do 210, sine of 210 is -1/2. So this one's going to give me -2 for my R. So when I go 210, I go -R, and that's both 210 and 30 degrees. Both of them landed on the same dot. So it looks like this does the circle twice. All the signs are going to be negative, and we're going to have a negative radius. Does this look like, it looks like a circle, right? So like the diameter is 4, which means a radius of 2. Which means if I went up to, like, the center would be at 0, 2. Does that look about right? We're going to check it. We're going to check it by like writing the equation of a circle at that point and seeing what happens when we switch to polar. So when you do a circle, remember, like x squared plus y squared equals r squared is centered at the origin. X minus h squared plus y minus k squared equals r squared is centered at hk. So if I think the center is 0, 2, I have x squared plus y minus 2 squared equals r squared, which is 4. If I switch to polar, what do I get? The x squared turns into r squared cosine squared theta. This one's a little more work. We need to multiply it out. I'm going to get an r squared sine squared theta. I should get minus 4r sine theta. Plus 4 equals 4. Let's pause and make sure everyone processes that, gets it down and understands it. Well, it looks like we could subtract 4 from both sides, and those are going to go away, leaving a 0 on the right. So I've got r squared on 2 things over here. I'm going to factor out the r squared. And what is cosine squared plus sine squared? 1. So this turns into r squared minus 4r sine theta equals 0. Did you just yawn, Dad? Am I boring you? Rude. F. I can factor out an R. And now we've got two factors equaling 0. We set both equal to 0. And I get R equals 0 or R equals 4 sine theta. But R equals 0 does not work for the, doesn't even make sense. That's just doing 1 point. That's a waste of time. And look at that. Boom. We were right in our guess. Well, my guess. If you guess the same thing, good. How many of you remembered this form of the circle equation with the H and the K? The center shifting. Yeah, I bet it's been a while. I'm sure. I don't know that you use it a lot in Calc 1. Not a whole lot in trig. So like algebra. What?
I don't know if we use that.
Yeah, I don't even know if you use it in Calc 1. I can't recall doing it. So, and we saw that on the other picture. A circle could either be a cosine theta or a sine theta, and it just changed where it was. But memorizing where it is only, you could fuck up what it, your memory could be bad, and it will be, unless you have perfect memory, eidetic memory. You're not going to remember the shit in 6 months. So it's doing this plug and chug is really the best approach. And it's kind of how you're going to have to do parametric shit in Calc 3. So that's really what we're grinding out here. Any questions on that one? Okay. Let's see. So we had limacons. These were fun. Weird fucking little thing on them. This had 3 kinds. You have one that has a little inner loop on it. One that makes a heart that like hits the origin. The dent is at the origin. And we also had one that kind of like made a dimple, didn't hit origin. And trying to remember these is fucking not worth your time. We're remembering which one's which. I'm going to throw up 3 equations. We'll just grind out some parts real quick. And the heart is called a cardioid. So let's make a little theta R table. Why don't we just stick with increments of pi over 2, make this quick. We know it's going to make some shape like this. So like we can expedite how quickly this goes. For all the ones where it's a multiple of pi, sine is 0. So this just turns into a 2 for each of those, right? I stick in pi over 2, that's a 1, these become 4. What does that look like? I think I skipped some shit that I need. No. Theta is 0, I got a 2. Yeah, I don't know that I have enough here. This looks weird. This can't be right.
How's 3 pi over 2 4? 0?
0, there it is. Thank you. I'm like, I should have a fucking 0 here somewhere. That's exactly what it is. Thank you. I fucking got rushy in my head. That would be -1, and so we get 2 minus 2. My head was blowing up here. I thought I didn't know what the hell I was doing. So it looks like it's doing like this. Comes down, hits there again, does some shit like that. So this was a cardioid. I mean, my noodle was baking there. I'm like, what the hell is going on here? We do that here. R is just 1 larger, isn't it? All I got to do is increase my R by 1 on each of these. Don't I? This is the only thing that's changed between this graph and this graph. 2 is 3. So instead of adding 2, I added 3. This should be 3, 5, 3, 1 now, and 3. Right? So if I call this like RA, this is like R equals 1 plus RA. Basically. That saves us a little time in plotting those points. Well, at least in figuring out what they are. Looks like I need to go up to 5 circles here. So when I have 0, it's 3. Pi over 2 is 5. 3 here. We don't go to the origin on 3 pi over 2. This looks like it's got the dimple going on. That kind of thing. That one had this kind of thing going on. And it may not even spike like that. It might just be more smooth. I don't know. Without plotting more, I don't know. It might spike there. It might, I think it's just got like a little dimple going on. We make our table for this one. Should have 2 on those. This one should be 5. And 3 pi over 2 is going to be 2 minus 3 is -1. There's some point here, let's see. Does 3 sine theta ever equal -2 where r is 0? There must be some angle. Sine theta equals -2/3, that's less than 1. So there must be some angle theta that has it where we're actually hitting 0. Because this setup would give us r equals 0. So sine inverse. Again,
I'm getting negative 0.729 going on. I don't have it in.
there's some value. What's going on here is, let's see, make our circles again. And do one more thing besides graphing after this. Because graphing is only half of what you need to take into Calc 3. And like the lesser half, if I'm being honest. All right, so let's do this. We've got 2 on that one, 5 on this one, 2 on this one. We got a -1. It's doing this. Some point it hits 0 and comes in like that and does an inner loop. We know it hits 0 somewhere. Sine theta is going to have a -2/3 at 2 spots. So this makes the inner loop one. You're really just better off plugging as many thetas as you need until you start seeing that the points are hitting the same spot. Like on the circle we did, as soon as I went past 180, 210 started hitting the same points. When that starts happening, you're just tracing over the same graph again. What about r equals 3 over 2 plus 2 cosine theta? Good to know. I really don't have an interest in making a theta r chart here. So practicing switching to X and Y is helpful just sometimes because it's easier to draw. So if we cleared fractions, I get 2r plus 2r cosine theta equals 3. R by itself is square root of x squared plus y squared. And r cosine theta is what? That's just x, so I get plus 2x there. So maybe I'll subtract. I don't like this square. I'm going to subtract the 2x over. And if I divide by 2, I get square root of x squared plus y squared equals 3/2 minus x. Probably would have been easier to square earlier, and I got a fraction, I got a fucking square. When I square this, square both sides of this. Let's see, I'm gonna square it. The same as doing that. I'm gonna have a 9/4. I'm gonna have a minus 3/2 x, and a minus 3/2 x is a minus 3x. And then plus x squared. Right? That look about right? I got x squareds on both sides, so I can subtract those out. I get y squared equals 9/4 minus 3x. I could actually, if I factor out a -3, this is x minus 3/4. This is a parabola that opens sideways. And the center, it's positive. No, it's not, going the wrong direction. X minus 3/4 is putting the 1, 2, 3, 4. That's like 1. 3/4 is right there. That's the vertex, and it's opening to the left because it's negative. And I could be more specific if I needed the actual points. Let's call it a wrap right there. I got another one, but we're gonna do it. We'll treat it as a warm-up for Monday. Unfortunately, Mondays is important. Like if you're wanting to take the week off for Thanksgiving, you're risking that Zoom doesn't record. But you're all presumably adults. I don't think I have anyone under 18. That looks like he might be under 18. He's got that baby face going on. You're all adults, so you can choose whether or not you're going to be here on Monday. I will be here lecturing on Monday. If you don't, you're going to have to catch it, watch it after Thanksgiving, but before we have a test. And it's on arc lengths and surface areas using polar coordinates. So how does those change when we switch to theta and r? Have a good weekend. I am at the Mesa Center from 8 to 2 on Saturday. If you're wanting to work on Calc 2, just as a reminder.
We're down to only 7 full blank pages left in this.
Looks like you're gonna be fine.
Yeah.
We only got one more topic.
Perfect. That's by far the closest I've ever cut it.
That's why I hate using those, because like if I get one that doesn't have enough pages, I'll try to aim for like the 100 or 120 pages.
That's the how many pages is it? I think it's one subject notebook college rule. 70 pages.
Oh, wow, that's light.
Yeah.
Yeah, for math classes, I like getting, when I get them, I prefer the graphing ones,
The graphing ones are so much nicer,
but they're more expensive.
they're not much more expensive. I already had this one, so it's like,
Yeah,
do I
but-
go buy a new one or do I use one I already have?
But you do have to take non-math courses
I
where
do.
graph paper doesn't help, and that is perfect.
Oh, yeah, but I've got, because, so it was on sale a couple years back, right? And there, so I have 2 siblings. And so we're all in a high school, my older sister, college a couple years, so we just found a stack.
I did too, and I still fucking have them. I know exactly where they are. They're on the side of my desk. There's a pile of fucking dust on them. Cause I haven't been a student in a long fucking time.
But so, we got like a good 10 more notebooks at least. No, we're gonna burn through them all, cause I got years left of college